I'm a hardware engineer. I design computers, and it's really fun to be involved in deep learning today because the computers are really the enabling technology. We've been working with lots of people doing language translation, speech recognition, vision in general, vision for self-driving cars in particular. What we've observed is almost all of the algorithms have been around since the 1980s. The convolutional neural network, which is the dominant thing for both speech and vision today, was written about by Yann LeCun in 1989. And so the algorithms were around, and there are two things that were missing why the first approximation, neural networks were a curiosity in vision until about 2012, when they came into prominence by winning the ImageNet competition. The first was there wasn't enough data. And without a large data set, I'm showing sort of the ImageNet data set up on the right there, you couldn't train a network. It would overfit to a small data set and not generalize well. And so you needed to have lots of data, but they had the large data sets by around 2005. I'm not counting things like MNIST, which are kind of toy networks and aren't really relevant to the current discussion. So it wasn't until 2005 that they had the data, but neural networks still didn't take over. People were still using Hog and SIFT and all of the usual old school computer vision things, and the speech recognition people had manual phoneme detectors because they didn't have the compute. What really made it possible to have AlexNet win the ImageNet competition in 2012 was having the horsepower of GPUs able to train these networks and make them possible. So I spend a lot of time now going around talking to the people who use our GPUs, this is my NVIDIA hat on, and ask what they want. What I find is we're still the limiting factor. This is a great quote from the Lavin and Gray paper, which is really about using Winograd transforms for convolutional neural networks. But the observation they make is, like somebody said earlier, your graduate student has a great idea, they want to train a network. People limit themselves today to what they can train in a week. That's kind of the threshold. There are people who have larger network ideas they would like to try, and they have larger data sets. By the way, the two go hand in hand because a larger network typically has a larger capacity and requires a larger data set to train, and they don't do them because they can't train them in a week. So very much the pace of what we can do with neural networks today is limited by what the hardware can do to train them in the threshold amount of time that people are willing to wait to train them. So the usual thing, and I've been doing parallel computing since the 1970s, is if you want to go faster, you use more processors. And there are few problems that are as conducive to parallelization as neural networks. If you look at a typical convolutional neural network, you have literally hundreds of millions of operations that can be performed in parallel with no dependencies between them. Every multiply of every convolution on every channel of a given layer is an independent operation. There are few problems that are as regular and as easily parallelized as this. And for training, it's even better than that, because for first order, what you can do is simply make 2 copies of your network and feed half of your data set to each. And in extreme cases, people will basically make 128 copies of their network, partition up their data set, feed them to each. Of course, you have to share the parameters between these because they're learning the same set of parameters, and each of these copies has to learn what the other ones have seen. For inference, you can't play this trick, right? You get one image and you have to say, there's a tree in front of your car or not. But even for inference, you can do model parallelism, where you can take these convolutional layers and chop them up. And especially today, where people have moved to very small convolutions, typically 3 by 3s or smaller, there's only a single pixel halo that has to be exchanged between the processors, or I should say shared between the processors, not actually exchanging results. They're sharing the activations from the previous layer. So it's quite easy to parallelize these to very high levels with minimum communication and very simple synchronization. So if you want to go fast, you use multiple processors. If you want to be efficient and fast, you use GPUs. I will take exception to what somebody said earlier about, these GPUs are hard to use. The reason why everybody uses these GPUs is, in fact, they're quite easy to use. I encourage you, if you want to program them, to go to the CUDA tutorials. We've had great results having people come to our booth at various shows. We have GTC coming up in April, and taking a 1-hour course. They put the headphones on, there's individualized instruction at a screen, and write meaningful CUDA programs after an hour, if they're a competent programmer to begin with. So it's quite easy to program them, but for neural networks, it's even easier than that. We have a cuDNN library, and what everybody does is they take the library, and they don't actually have to write the CUDA code. They simply make some calls to the library, and it does all of the things you need to build an arbitrary neural network. It's what's embedded in Caffe and Theanos and Torch, and all of the major frameworks use GPUs, and it actually is quite easy. Our current state of the art, I wish I could say more about what's coming. There'll be some announcements around GTC about our Pascal generation, but I put under strict rules not to say anything about it here. I'm going to say that it's going to be many times better, not just 2x. But the current state of the art is if you buy a Titan X, and this is what either in this form or in the M40 form, which is basically the same thing, you get 3,000 CUDA cores running at a gigahertz. That's 6 teraflops of 32-bit floating point. To put that in perspective, that was sort of the fastest machine in the world in the mid-1990s with 6 teraflops. So you sort of 2 decades later, you can put it on your desk and devote it to training your neural networks. That's 24 gigaflops per watt. That's in a 28 nanometer process. What's really exciting for people who deploy these neural networks and things like self-driving cars is our Tegra X1. This is what's in our Drive PX computer that's being used by a bunch of different auto manufacturers to be the brains of their self-driving cars. And this is a smaller number of CUDA cores, but one thing we've done, and it's sort of along the lines of the talk on approximate computing, is we put in very strong support for FP16, and this is something that you can expect going forward in a broader range of products. And by doing this, we're able to get a teraflop. That was a CM5, the fastest machine in the world in 1993. Was a teraflop. You can now get it and hold it in the palm of your hand and have it dissipate so little power your hand doesn't get hot. So for about 10 watts, we can do a teraflop, and that's 100 gigaflops per watt. And this is an amazing machine for building inference engines for revision and speech and a number of other things. To give you a comparison, CPU to GPU, here's a comparison of Titan to a Xeon. You get sort of 7 times the performance, roughly 5 times the efficiency. And by the way, I should say that's comparing 28 nanometer process to 14 nanometer process. And with the Tegra, it's about 11 times the efficiency. And you have this little 10 watt handheld chip beating the 150 watt CPU quite soundly. Now, if you really want to train things rapidly, 1 GPU is not enough. The current state of the art in training is reported by Baidu at NICE this past December. With their Deep Speech 2 network, where they're able to efficiently get essentially linear speed up to 128 GPUs, and get the training time in seconds, down to about 1,000 seconds, less than an hour, to train a number of these networks. So GPUs are fast, but we weren't satisfied with that. And in particular, we were looking at the problem of putting networks like VGGNet or AlexNet into mobile devices. And what we found is it almost didn't matter what we did with the computation. Doing the sort of 16-bit precision multiply we needed to do inference on these networks takes just a few picojoules. Reading one 32-bit coefficient from memory takes 600 picojoules. So there's sort of a 200 to 1 cost ratio between reading the coefficient from memory and doing the computation. So it almost didn't matter what you did on the computation side of these machines. We had these networks with on the order of hundreds of millions to billions of parameters. It would not fit in on-chip memory. And reading these parameters in was the dominant energy cost. There was zero reuse. You for a fully connected layer, you would read the parameter in, you would do one multiply and not use it again until the next frame. For inference tasks, you're not able to batch, right? You can't take 60 frames and queue them up and then process them all at once because you'll have hit the tree, but before you get done assembling the batch. You actually need to process each frame real time. We typically have very hard real-time constraints on these image processing tasks. So we started working very hard on how we could reduce the size of the model. We wanted to see if we could take these models, which when we started were on the order of about a gigabyte, hundreds of megabytes to gigabytes, and see if we could get them under a megabyte. And I'll show you that at the end of this sequence that we were successful with that. So the first thing we did is we revisited an old idea. It turns out all of these ideas were developed in the 1980s, and since it's neural networks. So Jan LeCun wrote a paper in the late 1980s or early 1990s called Optimal Brain Damage, basically how best to prune your neural networks. And his method actually used the Hessian and taking various second derivatives and finding minimums. For an MNIST network, you could do that. For the modern networks, that's just way too computationally intensive. So we took a simpler approach, which is we basically trained the networks. We found which weights were below a threshold, and we pruned those off. And what we discovered is we got a result much like what happened to HAL in the movie 2001: A Space Odyssey. Our networks got very dumb. That's sort of shown here by the purple line. We pruned even just a few of the parameters off, and our accuracy dropped unacceptable levels. Our criteria here is we wanted to reduce size with no loss of accuracy. But the insight was that if you then retrain the network, constraining the neurons that you've pruned to remain pruned, they can't grow back, you can actually recover the accuracy and in some cases get better accuracy than you originally had. And if you iterate this process on a network like, I believe these are results for VGGNet, you can basically throw away 90% of your weights and lose no accuracy. And so this was a pretty good result. We were able to get from sort of, gigabyte-sized networks down to 100 megabyte-sized networks. That was really good. This shows the results for pruning VGGNet. And what you see is the bulk of the weights are in the fully connected layers. In fact, the first fully connected layer is the bulk of the weights. That layer gets pruned almost 95%, which offsets the fact that the convolutional layers don't prune as well, but you can still throw away 2/3 of the weights in the convolutional layers. We've applied this to a whole pile of networks. One of the ones that I thought was kind of amusing was applying it to neural talk, where we're pruning not convolutional layers, but recurrent neural network layers and along short-term memory. And it's interesting how, as you prune things away, the text that it generates changes as it sort of loses some of its cognition. I'm not going to go into detail here. You can look at the NICe paper for details of this. Now, it turns out we were doing this looking at building special purpose hardware. We found that there were two immediate ramifications of it. The first of which is if you just took this and ran it on either a CPU or a GPU, it ran 3 times faster. Even though the sparse networks, the sparse matrices, aren't a good match for either CPUs or GPUs. I mean, the CPUs, to get performance on this, are using their vector units. They want a dense matrix to be efficient there, and the GPUs work better on dense matrices as well. But because both of them were so memory dominated, by going to the sparse representation and only having to read 10% of the data, we didn't get a 10x improvement, we got a 3x improvement. It more than offset the irregularity created by the sparseness. So starting there, we took the next step, which was we asked ourselves the question, how many bits do you really need to represent a weight? And we approached this as sort of information scientists by saying, what we really want to do is a scalar quantization, but not the traditional scalar quantization where you divide the space up and quantize in even points, right? So you could have a weighted binary representation or something like that. But we simply wanted a code book. We give ourselves, if we have 4 bits, we get 16 code words. We wanted to find the optimal representation for those code words. And like everything in neural networks, the way you do this was with stochastic gradient descent. So what you do is you initialize your code book, not to random values, but to seeded values, say, linearly distributed, or in some cases we will sample by where there are more neurons, we'll put more values. But then we'll run the training algorithm to train the code book. I mean, anything you can take a derivative of, you can train with stochastic gradient descent. And so you can train your code book. And the end result looks like this, where you'll start out with a bunch of weights, here which are independent 32-bit floats. We initialize the code book by doing k-means clustering of these weights. So we basically look at where the weights are. We cluster them around certain points, given a certain, say we have 4 bits, we'll have 16 points. We'll then basically have each weight replaced by its code. A 2-bit code that says which of the 16 entries in the code bits you are. That code will look up the centroid, but then we will run stochastic gradient descent. As we find our errors, we will use those errors to backprop, take the derivative with respect to the code book, bump the code book entries up and down, and actually by fine-tuning the weights, we can basically get by with far fewer bits than if we restricted ourselves to have evenly spaced quantization. So we refer to this as train quantization. What you see here is the distribution of our weights. You'll notice that this is after pruning, so it's bimodal. If you took an unpruned network, you would have more of a normal-like curve here, but it turns out all that stuff in the middle of the normal curve doesn't matter. Those weights aren't doing you any good. So we prune all of those out. You take a look at what's left. You do the clustering and then training, and you get these little red points here. That's our final representation of the weights. And it's just a far more efficient use of bits than the little green X's, which are what you get if you took the same number of bits. In this case, I think it was 5 bits, and just used a linear distribution, because you're sampling out here where there's nothing interesting with lots of points, whereas the train quantization puts the points where they can do the most good. It also has this property that the network learns around the constraints of the quantization. If you're limited to 16 values for your weights, it will change how it actually does the convolutions and how it does the fully connected layers to get the most accurate learning it can with those weights. And this graph sort of shows the ultimate result of that learning. It turns out if you want no loss of accuracy, the convolutional layers can be represented with 6 bits, and the fully connected layers with 4 bits. But what you see is if you're willing to accept just a little bit of loss of accuracy, you can actually live with 4 and 2. You can get by with amazingly few bits per weight. So if you combine the pruning, this is the pruning only is the purple line here, with the quantization, we're now down to about 3% of the original size of our network. We started with a network of about 1 gigabyte. We're now down to about 30 megabytes. And by the way, around this point in time, I got a nice email from Andrew Ng at Baidu in Stanford thanking me for this work, and it actually pointed out an application of it I hadn't thought of, which it turns out if you're putting neural networks in mobile applications, you're limited on the size of the network that you can download. In fact, people won't let you download over the cellular networks more than 100 megabytes. But by applying these, in fact, I think like a week after we had this on archive, Baidu had an implementation and was putting it in practice, compressing their networks so that people could download their networks in mobile apps. And that wasn't actually our purpose of this. That's sort of the first one here, but we hadn't even appreciated that application at that time. So you take a gigabyte network, it's now 20 to 30 megabytes, you can download it on your cell phone. We did it because we wanted to reduce the memory bandwidth by 30 to 50x. But more importantly, if you're trying to deploy a neural network in a mobile device, instead of having to read a 640 picojoule per word from DRAM, and by the way, that's an LPDDR DRAM. If it's SDDR, it's many times that much, I think about 4 times as much. If we can read it out of a very local on-chip SRAM, it's 5 picojoules per word. And so by reducing the size of our working set by a factor of 30, we don't just win by a factor of 30, we win by a factor of something more like 3,000. Because as you basically drop the working set size so it fits in a lower level of the memory hierarchy, you reduce your energy cost of accessing that memory by orders of magnitude. Now at the same time we were doing this, Forrest Orlando and Kurt Koitzer and a bunch of people at Berkeley were pursuing the same problem from a different direction. They developed a topology they call SqueezeNet, which is a variation on GoogleNet, where they basically use a 1x1 layer that basically has more input channels and output channels. So it squeezes the activations down to a smaller number of activations. And then they use a parallel 3x3 and 1x1 to expand that back up. And they did a search over the design space of this and were able to reduce the size of the network comparable to what we did without having to do any pruning or any quantization of the bits. So I talked to these guys and I said, this is sort of what, really great stuff. And why don't we sort of put these two together and sort of like chocolate and peanut butter, it'll be better than the sum of the parts. And in fact it is. And this is sort of the ultimate thing. We started out with AlexNet, which is about 1/4 of a gigabyte, 240 megabytes. And the first ones of ours were basically doing the pruning, got it down to 27 megabytes. Applying the train quantization got it down to 6.9 megabytes. SqueezeNet by itself got it down to 4.8, so comparable to the 6.9. But then we took SqueezeNet and we basically applied the deep compression and a few iterations of that. We now have, this is actually an old result, we now have it less than a half a megabyte and getting, getting actually slightly higher accuracy than the original AlexNet. You'll see the original AlexNet was 57.2, we're at sort of 57.5 top one, and the 83 top 5 remains unchanged. We have comparable results for VGGNet and a number of other networks as well. Now it turns out this is wonderful even if you're running on standard hardware, but we wanted to also ask the question, what is the best you could do deploying this in a mobile device? And it really came to the fact that some of the techniques we're applying, in fact, the two techniques we're applying, doing sparse matrices rather than dense matrices, aren't a good fit for standard hardware. And using these sort of coded things puts a code word lookup and decode in the middle of your critical loops, which doesn't fit very well into either the vector units of CPUs or into GPUs either. You're having to sort of look up, basically look up tables in memory to do this decoding. But if you're building special purpose hardware, these things are trivial to do. So we now is with my Stanford hat on. A couple of my graduate students at Stanford and I, in collaboration with Mark Horowitz and some of his students, decided to build an ASIC for this. This is in an ancient CMOS technology, a 45 nanometer CMOS technology. But the key aspect of it, and you can really kind of see it here, is it's all memory. And in fact, the really nice attribute of it is everything that is operated on is fetched from a memory that's within a few hundred microns of where it's used. There's almost no communication cost in this unit. We take the sparse matrix and we distribute it interleaved by rows across the processing elements. This shows a 16 PE configuration. We get linear speed up to 256 processing elements. Each of the processing elements is shown here, and the basic operation is you have a set of activations. It turns out, I've been talking about exploiting the sparsity of the weights so far. We get our compression by throwing out 90% of the weights and then compressing them by a factor of 3. It turns out actually that you can also exploit sparsity in the activations, particularly for networks that use a ReLU as the nonlinear element. Only about a third of the activations are non-zero. It turns out that most of what your GPU is doing when you're basically doing inference on a neural network is multiplying something by 0. And you can save an enormous amount of work by just not doing that because you know what the answer is going to be. And so what we do is we basically store the activations, and again, they're interleaved by the row of the matrix. So every one of the P's, say I have 256 P's, has 1 over 256 of the activations for a given layer. We basically have a pair of buffers that we flip-flop layer to layer with those. And we basically have a leading non-zero detect after our nonlinear element there. So we basically are looking for the first non-zero element. And in fact, we have a distributed leading non-zero network. So every one of the PEs sends up its first non-zero. This distributed network then finds the first non-zero globally and distributes it to everybody. And that's the only global communication. It's very cheap because you do it once per row. So you basically think of your sort of scanning down your activations. You find the first non-zero activation. You give it to everybody. Now everybody multiplies that activation by their part of the column. And so you do that once per per whole column. The fully connected layers of VGGNet are 4,000 elements in the column. Even after pruning, it's 400. You're amortizing that one global broadcast over a lot of operations. Everything else is completely local. At that point in time, you've received the non-zero activation from that network. There's a queue here because the amount of work per element is different depending on how the non-zero patterns of the weights falls. And so we allow things to get very much out of synchronization until they need to be synchronized by having a certain amount of buffering. In that queue, we look up our sparse matrix representation, which is a compressed sparse column format. That's the correct format to use here because it basically allows you to exploit the sparsity of the activations. If you do compressed sparse row, you can't do that. And so we look up the column start and end for the interleave on this processing element. And basically, the overhead of the sparse matrix gets hidden under a couple of very simple hardware units so that we basically feed the weights then. We can look up the weights in this sparse matrix memory, which is most of the area of the processing element, very local read, and it goes into a weight decoder. We can, again, hide the complexity of the decode from this 4-bit trained quantization to a full, in this case, 16-bit representation by this weight decoder. At the same time, we're looking up the address for what we need to sum that into for the output activation. The multiply and add happen, and the multiply and add dominate the stuff that's not memory here because these special purpose units for walking the sparse matrix and doing the codebook lookup are actually quite trivial. And we basically get 2 operations per clock cycle on this unit. You can look at the area here. This paper has been accepted for the International Symposium on Computer Architecture this year. But it basically is able to do sort of 2 operations per cycle per processing element. And if you compare the GOPS against previous hardware accelerators for neural networks like the Dadian Now work coming out of INRIA and Tsinghua, what you'll see is our GOPS number is about an order of magnitude less than theirs, but our frames per second number is about an order of magnitude higher than theirs because we're, by exploiting the sparsity of the activations, gives us a factor of 3, and the sparsity of the weights gives us another sort of factor of 10. We wind up being about 10 frames per second faster, and actually better than that in terms of energy efficiency, even though we're doing fewer GOPS. It's basically working smarter rather than working harder. This shows the speed up numbers for our efficient inference engine. The geometric mean compared to a CPU is around 200x. Compared to the GPU without compression is about a factor of 50. The GPU with compression, it's more like a factor of 6 or so. The more interesting number, if you're interested in mobile applications though, is the energy efficiency of this approach. And compared to CPU number, it's 24,000 times better. And that's really the power of capturing locality. If you can keep your weights local, so they're sitting in this RAM right next to your arithmetic units, the memory energy, which dominates the energy cost of the computation, is reduced not just by the fact I'm making 30 times fewer references because I'm compressed by a factor of 30, but each of those references takes 30 times less energy. So now I'm getting sort of a 1000x advantage right there, and then the additional advantage comes from the specialization. Even compared to GPU, which is quite good, we're still on the order of about 1,000 times more energy efficient. So let me skip over this and kind of go into a quick conclusion here. So it really is exciting to sort of be in an era where hardware is in many ways the driving factor. I view it as an enabling technology. The real value in these neural networks comes from smart graduate students who think up new network topologies, new ways to train them, ways to get off saddle points. But for them to test those ideas, they need to have fast hardware. It's also interesting to think that the real difference between now and when Yann LeCun came up with the original convolutional neural network right around 1990 is really machine performance. But that performance is really coming to a halt with the end of Moore's law and Dennard scaling. So in 1990, you could buy a CPU which would have a performance of 100 spec int. I see lots of blank stares because you guys aren't computer architects. View that as an arbitrary measure of computer performance. Today, you can go out and you can buy a CPU core. In fact, you can buy a CPU chip with 6 to 8 cores that are 30,000 spec int. So each core is 300 times faster, and you get almost 10 of them on a die. So you're up to 200,000 times what Yann had to play with. If you get a GPU, it's basically another 10x. So you're up to 2 million times that performance. We have ways you can train pretty seamlessly with 128 GPUs, which gives you 256 million times the performance. And special purpose hardware basically gives you another 100x over that. So that 25 billion times the performance is really what enables you to do kind of exciting stuff today. What worries me is with, a lot of people haven't sort of internalized it yet. It's sort of kind of like climate denial. That CPU scaling has come to an end. New process technology isn't making CPUs any faster anymore. And so I'm worried about where the enabling hardware is going to come from for future generations of neural networks. But in the meantime, what should you guys as neuroscientists do? Well, of course, with my NVIDIA hat on, you should buy GPUs. If you're training, the best thing you can absolutely do is put together a cluster of 8 to 16, even 128 GPUs. It's absolutely the best performance per watt and the best memory bandwidth. And contrary to what some people have said, it is easy parallelism. It's quite easy to code up and get stuff working, with libraries or writing your own CUDA. It turns out most people today use GPUs for training. Only a few people are actually using them for inference. It's still the absolute best performance per watt and performance per dollar for inference in the data center. Companies like Baidu do this. Many people don't. I think largely through inertia. They got lots of CPUs in their data center and they don't have the sockets to plop the GPUs in. I think some of the most exciting applications are in Internet of Things, whether it's automotive or whether it's smart thermostats in your house that see where you are and turn the heat and the lights on and off so that we're not wasting energy where people aren't. You can get a teraflop machine with 100 gigaflops per watt to build your Internet of Things devices. I was actually at JPL yesterday giving a keynote talk at an internal function they were having, and I was telling the people who make the Mars rover, who actually built it with this sort of 100 megahertz CPU, which does happen to be radiation hardened and all of that, that the Mars rover could go much faster if they used Tegra X1. The thing goes at 1 foot per hour. That's just because their computer can't think fast enough. If you absolutely need the absolute best performance, you want to use an ASIC. And I think what we've found through our pruning train quantization study is, first of all, you want to start with a small network using the Berkeley squeeze net or something like that, where people have found the most compact network for a given level of accuracy. And then you can get basically another factor of 30 out of that through a combination of pruning and train quantization. And the real advantage of reducing the size of the model is locality. It lets you keep the working set of your model in a small enough memory that you can access it at a very low energy cost. So thank you, and I'll be happy to answer as many questions as the organizers want to give me time to answer.
Thank you. So why don't we do 2 questions now, and then I think we have a break and plenty of time for questions after the break, right? The whole rest of the morning is discussion. Yeah, Gert?
It's a very nice work. So one key aspect that you mentioned was this non-zero detector that you have there. Mm-hmm. Now, in a neuromorphic crowd, we would perhaps think of a non-zero detector as a spike detector in an event-based system. So how would you compare this architecture to, say, a spike-based or event-driven approach?
Yeah, so I've never thought of a non-zero detector as a spike detector. Let me try to go back to the EIE architecture slide. This is the world's worst user interface. Well, maybe not the worst, but it's up there. We really didn't look at spiking networks when we were doing this stuff because we're very pragmatic and we wanted to get good accuracy on our networks, and so we started with networks. You're off the screen. Oh, I'm off the screen?
Yeah, plug's on.
I plugged it back in. Oh well, you can't see what I'm showing you, but I'll just use words. We basically started with the winners of the ImageNet competition. First AlexNet when it won in 2012, and then later VGGNet, and then later GoogleNet. Those are things that use sort of continuous valued weights the original network's floating point representations of weights. There's no temporal aspect to what we're doing other than frame by frame. Within a frame, there isn't some notion of a time sequence of spikes. And I think that's a big difference. And it turns out for building things with CMOS hardware, it's really efficient not to have spikes because you can sort of take your representation, apply it, whether it's through the decoding operation or arithmetic operations like add and multiply. And those are just really efficient operations to do without a temporal dimension. If I add a temporal dimension, it requires me to toggle lots of things. And toggling lots of things dissipates lots of power. So we prefer to use continuous valued variables and not to spike in these networks because it's fundamentally more energy efficient. I don't know if that answered your question.
Well, I thought the non-zero activity detector is really a way of thinking of spikes, right? It's
Yeah, but it's not
you
detecting
don't do
non-zero
anything.
activity, it's detecting a non-zero activation.
Yes, exactly.
Yeah, but it's basically exploiting sparsity. A key attribute of what we're doing on both weights and activations is exploiting sparsity.
Thanks.
Yeah.